and I will not get finished with them, even if I don't say good morning. But we'll go as far as we can. I had wanted to cover a good deal about the holographic principle. We're never going to get there. What I would like to do... Yeah. Right. Oh, thank you. But what I do want to talk about is entropy in black holes and the string theory of entropy in black holes. But before I do, first of all, just an observation or two about what I think the general message of all of this is. The general message is, first of all, the concept of information is a good concept. Good meaning in the sense that it's conserved. Distinctions between configurations or distinctions between states are eternal, at least as far as I can tell. Another word for that is unitarity of the S matrix or of the time development. But the concept that I don't think is a good concept is the idea that bits of information are localized in space-time in an invariant way. Now you say, there's already something funny about quantum mechanics. An electron can be in a superposition of different places and so forth, so what does it mean to say that information is localized? Well, here's the sense in which I mean it. If you were to measure the location of an electron precisely in your frame of reference, and the frame of reference might mean moving on a railroad train or something like that, and then convey the information to me, I could then use that information about where you said the electron was to then predict in my frame of reference where the electron will be at some, not where it will be, but what its wave function will be at some later time. And in that sense, you will convey to me a bit of information about how a bit was localized, where it was localized, and my subsequent observations will be consistent with your determination of the location of the bit, quantum mechanics or not quantum mechanics. That's true in classical mechanics, it's true in quantum mechanics, it's even true in quantum field theory. I believe that is what is going to break down in quantum gravity, and we've seen examples of it. We've seen examples of it not on tiny scales of the Planck scale, but on huge scales. If a black hole has a size of 10 to the 9th light years, from one reference frame, a bit of information never crosses the horizon, spreads out over it. The same bit falls freely into the black hole from another frame of reference. And I think one way of describing it, ordinary relativity, which is also a relativity of perceptions, has to do with velocity of observers. I think this kind of relativity has to do with shutter speed, speed at which, or time resolution, the time resolution that goes into your experiment to determine where the bit of information is. And it seems from everything we know that the shorter the time resolution, the more the information is spread out over large distances in ways that are quite different, very, very different than quantum field theory. In quantum field theory, the faster your time resolution, the more precise you can say where a thing is. It seems, at least in string theory, and it's not just string theory. The conservation of information in black hole physics demands that. The horizon of a black hole is the place where you get to see things, where you get to observe things with enormously rapid time resolution, and that seems to be the ingredient which allows the different perceptions of different observers to be extremely different. That's something that people are having a very hard time getting used to. Getting rid of old quantum field theory prejudices reminds me of at one time when they discovered that the Earth was round, people used to say, well, yeah, maybe it's round, but I can't quite understand why the Chinese on the other side don't fall down. Why don't they fall off the earth? Well, you explain. Gravity pulls you toward the center and so forth and so forth. And you explain and explain and explain, and then the person goes home and says, yeah, but I can't understand why the Chinese people don't fall down off the earth. I think we're having the same trouble. We keep coming back to a quantum field theory view of things when we are trying to push into a region where I think quantum field theory simply breaks down. Not just quantum field theory, but the idea of localizing information in an invariant way. Okay, so much for sermon. Let me finish up one remark, an important remark, I think, about something that I talked about last time, how strings spread when they come near the horizon. I showed you a little film clip. Apparently, I kept showing the same film clip over and over. I intended to go from one to the next, but they all look the same, so it doesn't matter. Showing how, as something falls toward the horizon, this could be the horizon, how it spreads out. What I didn't tell you was much about the fluctuations in the location of a string in the other direction, perpendicular to the horizon. And I want to just mention that, or show you how it works, show you how to calculate it. And there's a little bit of a surprise. An elementary particle, as time goes on, as Schwarzschild time goes on, what I mean by an elementary particle is I mean a quantum field theory particle, or just a point classical particle, as it falls toward the horizon, as Schwarzschild time goes on, we'll get closer and closer and closer to the horizon. Right? A string won't. A string will simply hover over the horizon at about one string scale distance, never getting closer, at least as seen from the outside, at least as seen by the observer that has this enormously powerful time resolution. Okay, so let me show you how that works. And it is really the basis of the idea of a stretched horizon, that not only does nothing ever fall through the horizon, but if the world is made out of strings, nothing ever gets closer than a string length from the horizon, in a certain sense that I'll show you. All right, here's our standard picture. It's either ringless space or a black hole, it hardly matters. And I usually take this side to be the horizon and have things falling in this way. I thought of a variety, and just to confuse you, I would have things fall in this way this time. Here's a string, a closed string falling into a horizon. What I showed you last time is, first of all, let's introduce some coordinates. This one is called x plus. This one is called x minus. Sometimes x plus is thought of as time in the light cone frame, and I'm thinking about the light cone frame. The light cone frame is a frame of reference where x plus is the time variable, so I'll sometimes call it tau, and x minus is just the other light-like direction. How does this x plus variable relate to the Ringler time? I'm not going to try to draw a whole bunch of Ringler slices, but at least as you get very close to the horizon here, the connection between x plus and omega is that x plus is minus e to the minus omega. Don't ask me about units. I think I'm working with a dimensionless x plus, but I don't remember why. Which also is equal to minus e to the minus t over 4mg if I'm really thinking about a black hole. Okay? So x plus just continues right through smoothly and continuously, but omega goes to infinity at the point where x plus goes to 0. X plus goes to 0 from the outside is a rather special place, and the timelines sort of accumulate there. That's important to keep track of. That's why we get this enormous power of terrific time resolution when we look at the system from the outside. Okay. All right, so what I showed last time is that if you follow a string, taking into account more and more of the high-frequency normal modes that you can see, and when I say see, we would keep track of as it gets closer and closer to the horizon, the string spreads laterally or along the horizon I want to show you how it spreads in the other direction. And it's a little bit surprising. Okay, let me write down one or two equations. Here are the basic string theory equations, and as I said, they're about the only ones I really know. This tau is light cone time. This is light cone string theory. Oh, one last thing. In light cone string theory, the energy conjugate to this direction is really the mass squared divided by 2. It's not E equals mc squared, but it's E equals m squared over 2 in light cone coordinates. Of course, it's a different energy. It's just the energy conjugate to this variable. Okay, so this is the usual string theory equations. What is sigma? Tau, of course, is just time along this direction. Sigma is not x minus. Sigma is the variable that runs around the string from 0 to 2 pi. It's just a parameter which parameterizes points along the string. All right, this is not the equation that I want to study right now. Oh, incidentally, this is a two-dimensional quantum field theory, string theory. And in that string theory, in that two-dimensional quantum field theory, X is a scalar field, and it's a scalar field of mass dimension 0. Okay? That's why we got these logarithms when we studied the spreading of the string as a function of the small time cutoff. Now I want to do the same thing for the other direction. Actually, sorry, this direction, the x minus direction, and ask, as the string gets closer and closer and we see more and more normal modes, how does it spread out, or does it spread out, in the x minus direction? So for that, we need a formula for x minus. X minus is given by a constraint in string theory. It is not one of the x's that satisfies an equation like this. In light cone string theory, it's given by another rule. So let me tell you what the rule is. The rule, I'll write the rule, I'll write the equation for the rule, and I'll tell you what it means. If we call x minus the coordinate in this direction, then the rule is the x minus by d sigma, dx plus by d tau, tau being like time, plus dx plus by d sigma, dx minus by d tau, minus, I think it is, dxi by d sigma, dxi by d tau is equal to 0. I stands for the directions perpendicular to the horizon. Okay? What does this equation mean? I'll tell you what it means. This is the canonical generator of translations, not translations in space, but translations along the string. This is the canonical generator that generates translations along the string in quantum mechanics. And what this is telling you is that no point on the string is special. It's telling you the state of the string is invariant under reparameterizations along the string. All right, but let's simplify it a little bit now. Tau is, of course, the same as x minus. Tau and x minus are the same here. So in particular, the x minus by d, what did I say? Did I say that tau is x minus? I meant that tau is x plus. So the x plus by d tau is just 1, and the x minus by d tau is clearly 0. So the formula simplifies to just this simple formula, and it tells you how x minus behaves. It is the basic working formula for understanding how x minus behaves. Now, the only thing I'm going to say about it is it tells you the mass dimension of x minus. Mass dimension in the sense of two-dimensional field theory. The x's themselves are dimensionless, carry dimension 0. A sigma and a tau have in the two-dimensional analog theory, have units of length. All right, we can cancel this here. And what we find is that x itself, x minus, has units of 1 over inverse length, mass dimension 1 in the two-dimensional theory. what equals +1, and +1 means mass dimension +1, length dimension -1. Now, that immediately tells you, here's the game we're going to play. We're again going to define an average of x minus averaged over some time interval, some omega interval. Right? That corresponds to a little bit of tau. And so let's take here a delta tau. Delta tau, which is the same as a delta x minus. Delta x minus, and delta x plus. A little bit of delta x plus here. And I want to average the fluctuations in x minus over that little bit of x, over that little interval. I don't have to do any work. I actually did the work and found the answer by doing a bunch of arithmetic. Then I realized all you have to do is recognize that this thing has dimension +1. The answer can only be that the fluctuations in x minus squared, the average means averaged over this little time here. Two kinds of averages here. One average is just a little bit of a time average. The other average is the quantum average. That, on dimensional grounds, can only equal 1 over delta squared. Right? That's pure dimensions that x minus has, from this formula here, dimension 1. So that means x minus mass dimension 1. So that means this goes like 1 over delta squared. Well, what is delta? Delta is just a little bit of uncertainty or a little bit of a smear in x plus. So I can also write this as an uncertainty relation. Delta x plus, delta x minus, that's what this is, delta x minus, is equal to 1. Now 1 doesn't mean 1, it means L string squared, or alpha prime, because I've been working in units in which the string length scale is 1. Alpha prime is just the units in which, the units in which I'm working, and that's presumably somewhere near the Planck scale, but its actual value relative to the Planck scale depends on the coupling constant. There's two kinds of dimensions. No, there's real space-time dimensions in which the x's are lengths. Here, these? Oh, yeah. I'm missing some length scale here, which is probably 4 ng.
Is it alpha prime?
Yeah, the right formula there is alpha prime. The right formula there is alpha prime. You're right, I'm inconsistent in my dimensions, but the right formula is alpha prime. So this is a kind of non-commutativity, a space-time non-commutativity, delta x plus, delta x minus, which is of order alpha in free string theory. Now let me point out what this means geometrically. What this means geometrically is, first of all, as you push closer and closer, so that this little delta gets smaller and smaller, the fluctuations in x minus spread out. But exactly how do they spread out? They spread out on a hyperbola. Delta x plus, delta x minus, they spread out on a hyperbola as the string goes through. Now way down here, this isn't really right because the black hole formed someplace in the past. So way down here, the physics is different. But until we get down to that place where the black hole formed, the spread in delta x minus looks like this. And what is this hyperbola? This hyperbola is just the hyperbola, which is a distance L string, proper distance L string from the origin. In other words, it's one spatial unit away, one string unit away from the horizon. That string never gets closer The whole thing never gets closer than one string unit, and the edge, the trailing edge of it, if you like, never gets closer than one string unit from the horizon. The reason I bring this up is to explain that there is something real about the stretched horizon, at least as seen from outside, that unlike a point elementary particle, which doesn't fluctuate in this way, and which you would just say gets closer and closer, the fluctuations have this property, at least as reckoned in time units and in space units and so forth, as seen from the outside. So this is a curious, yeah.
So what happens if you send in a deep?
Say it again.
What happens if you send in a deep particle?
A deep particle. Good
Not a
question.
string.
Deep particles, of course, have a fuzz of string around them.
That's true.
Yeah, so I guess the answer is the fuzz of string. And you know, when you hit a deep particle real hard, or look at it real fast, what you see is that halo of string around it. So I think it must be the same, but yeah. But this comes up in other contexts, the same kind of delta x plus. Yeah. It's closely related to things that are Toaster said.
Since you haven't mentioned this yet, standard relativity interpretation of particle observer associated with the particle being memorized, he or she doesn't know there's an memorized.
Right.
So what happens to the string?
Oh, well, no, as far as somebody traveling with the string, they see, let's say they have a camera, they're taking a picture of the string, they don't get the advantage of this enormous time dilation. They see one mode, two modes of oscillation of the string, and they don't see it grow.
So they do observe it, but do they observe the memorized or not?
No, they don't observe, no, they don't see anything.
It's like a point cloud.
Yeah, it's just like a point particle. Let's just see the string is big, and as big as a. They don't get the advantage of this enormous time resolution. You don't need a black hole for this. If you had a camera that could take a picture of a string with extremely high time resolution, you would see it spread out and do exactly the same thing. But the black hole is the lens through which you can look and see this enormous time dilation. Okay, now I want to come to black hole entropy as calculated by string theory. For the most part, except for this little example here, I've tried to stay away from models and talk mostly about general principles. Today I want to talk about the string theory of black hole entropy, but I am not going to talk, since I've hardly talked at all about extremal black holes, I'm going to focus on Schwarzschild black holes, tell you what is known about the string theory calculations. They're the easiest ones. People seem to think there's something easy about extremal black holes. Much harder. And it's much easier to be precise about, if I get to the end, we will have a calculation of black hole entropy for Schwarzschild black holes. The reason they're easier is because the black hole horizon is just empty space. How could anything be easier than that? Okay, I'm going to do the calculation in d dimensions, just to show you that, that there's nothing, well, that it works in any number of dimensions. We start with a Schwarzschild black hole. Here's the formula for a Schwarzschild black hole. 1 minus r Schwarzschild divided by to the d minus 3 over r to the d minus 3. Okay, so if d is 4, this just looks like ordinary Schwarzschild. dt squared minus the same thing inverse the r squared minus r squared d omega d minus 2 squared. Only new thing is that instead of writing r Schwarzschild over r, you write r Schwarzschild over r to the power of d minus 3. Okay, what about our Schwarzschild? How does it compare with the mass? It's not just 2mg. I'm purposefully leaving out a bunch of numerical factors. First of all, I can't keep track of them because I cannot find them anymore. I have them someplace. But second of all, they don't play any big role. I'm not going to keep track of numerical factors. Our Schwarzschild is scales. The scaling of it is Gm. Now that would be in 4 dimensions, and then it's to the 1 over d minus 3. That's our Schwarzschild, and that goes into here. The area of the horizon is our Schwarzschild times to the d minus 2 times omega d minus 2. Omega d minus 2, of course, is the unit sphere in d minus 2 dimensions. And the Bekenstein-Hawking entropy. I will call it the Bekenstein-Hawking entropy because it has not yet been established that in any sense at all it has anything to do with state counting. So I'm going to distinguish state counting entropy from Bekenstein-Hawking, but the hope is, of course, to establish that they are really the same thing. So for the time being, this is just some stupid definition that Bekenstein and Hawking made up. Namely, the area is not stupid. Excuse me, I didn't mean to imply that it was. It's just some, for our purposes now, think of it as an arbitrary definition. We would like to establish that this has something to do with counting of states, and in particular counting of states in string theory. What else do we have to know? Oh, let's also write that in terms of the mass. Let's write that. We know it's our Schwarzschild. We have the area. We can rewrite that in terms of the mass, and that's going to be the working thing that we need to know. Without numerical factors, it's mg to the d minus 2 over d minus 3 divided by 4g.
Ladies, this formula is applicable only in D lattice and 3, or
Yeah.
because for
Yeah.
E equals to X,
Yeah.
you get
Only there are no Schwarzschild black holes in D less than 4,
have 2-dimensional holes.
but only in anti-de Sitter space. Yeah. So this is not anti-de Sitter space. Yeah. This is just plain flat space. Good old Schwarzschild, as Schwarzschild would have recognized it had he lived in deep dimensions. Some other little points. First of all, I am going to work in units in which alpha prime, which is L string squared, is equal to 1. Now that does not mean that the Planck length is equal to 1. We'll come to what the Planck length is in a moment. But in these units, the gravitational coupling constant G is equal to the string coupling constant squared, period. All right. And let's see, I think I probably ought to write down at this point the connection between the Planck scale and the string scale. Why don't I have it in my notes? Maybe I don't have it in my notes because I never used it. Oh, here it is. G is equal to L Planck to the d minus 2. Okay, so these are all the various relations. This is definition. This is connection between the string coupling constant, the joining and splitting coupling constant of strings, and this is the connection with the Planck length. Okay? Typically, if G is small, so is this G small then the Planck length is very small. Small compared to what? Small compared to the string length. You can also think of it the other way. If you like to hold the Planck length fixed, then as you let G go to 0, the string scale gets very big. Okay. Now we want to try to calculate the entropy of a black hole. So we need, of course, some kind of physical, not quite finished. Not quite finished with some string theory observations. One or two more things first. The energy of a string, the excited energy of a string. By definition, in the light cone frame, which is where I'm working, m squared over 2 is the energy, but in the light cone frame, string theory is simply a 1 plus 1 dimensional string, 1 plus 1 dimensional quantum field theory of a bunch of free scalar fields, d minus 2 free scalar fields propagating on a length equal to 2 pi. One can easily, just using the thermodynamics of finite temperature field theory, very easily calculate the energy, and that's pi times the temperature. Now, the temperature is a fictitious temperature that just will correspond to this light cone frame. It's going to disappear out of the equations for a minute. This is just some temperature associated with a fake 1 plus 1 dimensional quantum field theory. It's going to disappear in a minute. Times d minus 2, that's the number of quantum fields in the system. On the other hand, the entropy can also be calculated from this 1 plus 1 dimensional quantum field theory. You can get it from here, from dE equals TdS. Just use dE equals TdS, and you find that it's pi t, 2 pi t times d minus 2. The important thing that I want is the entropy versus the energy. And it's kind of obvious. The temperature is proportional to the mass. Take the square root of both sides. The mass is proportional to the temperature. The temperature appears here. And so what we find is that S is proportional to the mass. Now, that's crazy units, of course. What really ought to be here, there are various d minus 2s which I'm leaving out. The main thing is that the entropy of a string is proportional to its mass. And if you want to put some dimensions into it, you put out string here. There are other numerical factors which don't interest me right now. That's the main fact. The entropy of a string is equal to its mass in string units. Now, this is not too hard to understand. If you just think about a string wandering around in space, let's even simplify it. Let's think of it as a lattice string wandering around in space. Its energy, or its mass, is proportional to its length. All right? If I double the length of string, I double its mass. That's just additivity of energy in an ordinary frame of reference. On the other hand, what is the entropy? The entropy at every junction here, the string has the possibility of going up, going down, going back, going forward. That's 2 bits for every junction. And so clearly, the entropy is also proportional to the length. Mass and entropy both being proportional to the length. It just tells me that the entropy is proportional to the mass of the string. This is not what I want for black holes. What I want for black holes is over here. I want the entropy to vary in this way. Okay, so so far all of this is straightforward string theory. Now I'm going to introduce a physical hypothesis which at first seemed very strange to people, but has held up very well. Oh, no, let me, before, I keep forgetting little pieces of string theory that I need to tell you. All right, so one other little piece. There are subleading terms here. Subleading terms means things smaller than n. Let me tell you what they are. They're very simple. They're minus some constant which I don't remember. It depends on the particular string theory, times the logarithm of n. The reason I tell you about these subleading things is I want to show you why people say that in a thermal ensemble or an ensemble of strings, the most likely, by an enormously large factor, configuration is one single long string. Not a large number. Given a given amount of energy, given a given amount of mass, there is much more entropy or much more probability in one long string than in a bunch of short strings. Let me show you why that is.
So this logarithm n comes from with exponent in this current formula, or
Say it again.
logarithm n.
Yeah.
When you count the states, then it comes in this exponential, exponential factor in current formula, or
Yes.
Sorry, I'm missing the question.
no, I mean logarithm n.
Oh, where does it come from?
You count, yeah, very
Well,
It's just because
Yeah.
the string has to close us on itself, and it takes log n bits to specify, the starting place.
Oh, yes, that's right. Well, it's something like that.
It's
It's,
computer science.
no, I'm going to explain why. It's rather closely related to what you're asking. Right.
These are my kind of
It's
Look, if you ask me what the technical word for this is, it's probably got something to do with Carty's formula.
But doesn't this have to do with hagedon?
What's that?
hackathon, it's precisely hackathon.
No, this isn't true temperature. This is,
The
oh.
S is equal to N.
Oh, yes, of course, absolutely, absolutely.
And where do you drag out the C?
All right, you can calculate it in various ways, but the way to the simplest way to calculate
You
it.
have the number of modes and.
Yeah. You do the
You
you do the standard. You can do it by string counting, or you can do, but it's all the same. It's just 1 plus 1 dimensional field theory, keeping track of the subleading terms.
So now you want to compare hagedon with that.
Well, I don't want to compare hagedon with that. I just want to say, how would I compare this with the entropy of n strings, each one with mass m over n? Okay? All right, so what's the entropy of n strings, each with mass n over n? Let's call that S sub n of m. This is S sub 1 of m. S sub n of m is obviously n times S of m over n. All right, so what do we get then? The first term will just be m. We'll have n times m over n. That will be the same. So it will be m, and then minus n log m over n. Obviously, when m gets large, this is going to be dominated by the smallest number of n. Okay? And in probability, since everything gets exponentiated, this is a large dominance of the single string over many strings. I'll explain in another language why this is true. Supposing I have a certain, remember, mass is proportional to length of string. Okay? You have a certain length of string, and the question is it better to divide it up into a bunch of small ones or into one big one? Better in the sense of more states. Well, to every state that exists on here, I can chop this one up into an equal, chop it up into n pieces. For every little fluctuation that I can have on here, I can put the same fluctuation on here. Okay? Every little fluctuation on here, I can put the same one on here. So there's at least as many states here as there are here. But there are also long wavelength fluctuations on here that don't exist here. That's the origin of it.
And you can exchange also two pieces of the string.
You know, I know what you're talking about. I think when I calculated it, it was mostly just the effect that the wavelengths longer than this were the dominant
This
thing.
exchange doesn't play any role?
I don't think so. I don't think that played any role. But in any case, this is what you get when you work it out using John Carty's formula. So, and it does agree with this analysis here. Okay. So,
According to the second law, the universe should eventually evolve to just having one big string in it.
well, the universe is expanding, so
Yeah.
no, that's not the way I'm going to use it.
Okay.
The way I'm going to use it is differently. Here's how we're going to
The
use it.
assumption of an extensive entropy
Yeah.
is without gravitational interactions among the strings.
Yeah. Absolutely. And that's the only way we're going to use it. That's the only, absolutely. That's the only way we're going to use it. Okay, so now comes all of this is absolutely rigorous mathematics. Ah. No, it is. It's as rigorous as there's nothing in here that can't be done, with lots of equations. The rigor level, I suppose, depends on how obscure the derivation is. And since I always try to expose all the mysteries, I'm accused of not being rigorous. But it can be done in ways which are extremely mysterious and which you never understand. And so I guarantee you that there are ways to say this that make it very difficult. All right, what's the physical hypothesis? The physical hypothesis, let's start with a black hole. Now, there's one thing, again, something I haven't told you about string theory, but which most of you know, and that is that coupling constants in string theory are not constants. They are things which can be changed. They can be changed by changing the boundary conditions. I'm not talking about string theory with fluxes and fixed moduli. I'm talking about the simplest string theories which have dilitons. The dilaton is a field. It's a field whose value is the coupling constant, and it's a tunable parameter. It can be used as a control parameter. A control parameter means when you have some system and you want to slowly vary something, maybe adiabatically vary something, you want to turn a knob and follow the system as you turn the knob, that's called a control parameter. The dilaton, or the coupling constant G, is a control parameter. Now, supposing my black hole starts with mass m0 and coupling constant g0 squared, or g0, whichever you like. Now I start turning down g0. What happens? Gravity switches off. Eventually, g0 will get so small, it will eventually go to 0. What will happen to this black hole? It's got to turn into something. What can it turn into? The only thing that's available for it to turn into in the limit that g0 goes to 0 is string. And the reason is because everything else in string theory becomes infinitely massive in the limit that g0 goes to 0. D-branes, monopoles, everything else becomes infinitely massive when g0 goes to 0. The only thing left when g0 goes to 0 is strings, meaning free strings. So this must turn into a collection of free strings. How many free strings? Well, the statistical distribution is dominated strongly by one string. So the hypothesis, the speculation, the conjecture is that when a black hole, when the coupling constant in string theory is turned down, the black hole will, of course, expand. Gravity stops pulling it together. It starts to expand. It starts to blow up. And what will it blow up into? The most likely thing for it to blow up into, on statistical counting grounds, is just a single string. Now remember, a black hole is in some sense the largest entropy for a given mass. The single free string is the largest entropy for a single mass in the limit that g goes to 0. So the hypothesis is that these will go back and forth into each other under turning the control parameter g0.
And that's all. The big G is equal to little g squared.
Yeah.
And you did that with the string theory by watching the spin 2 sector.
Sure, of course. Yeah.
Small shell black hole, all the masses are pi to the 0 is singular.
Say it again.
For a small shell black hole, all the masses are pi to the 0 is singular. And what happens to the singularity?
Who knows? The hypothesis is, that we're working on a basic hypothesis, that black holes are seen from the outside are things that satisfy the laws of physics. The laws of physics tell us that a thing can't disappear when we change a control parameter. In fact, when we change a control parameter sufficiently slowly, the adiabatic theorem tells us that the entropy can't change. The hypothesis here is stop thinking about such things as information is really at the center of the black hole, blah, blah, blah. Think of it as a conventional object, and let's see how far we can go from the outside by using the standard laws of physics.
But the laws of physics break down at a singularity. So how can we talk about
I'm gonna,
laws of physics?
Well, what I'm trying to see, and having this
Yeah.
from the spin-through sector of
Yeah.
gravity, if I go the other way, from the string to the black hole,
yeah,
that spin-through sector,
yeah.
that's a kind of causing interaction of the string segments,
Right.
and it's making the black hole out of it.
Pulling them together. Yeah. And of course, you can calculate at what point it becomes a black hole by just calculating at what point it shrinks to its Schwarzschild radius.
But
Yeah.
can I ask something?
Mhm.
Usually, if you form a hole from the normal, it has something to do with zero modes, massless modes, yeah? Normal.
Wait, say it again?
Like baryons take normal particle.
Yeah,
They are non-massive excitation. The string, as you know, is zero mode.
right.
Now, if I form black hole,
Mhm.
why this black hole must have to do something with massive modes of the strings, and which we actually in fact never observed, because all of them have masses larger than the Planck mass.
Well, if you turn off gravity, it has to turn into something.
But not in one string necessarily. Or
But
even
well,
on the
that is
other.
why I went through this little exercise of showing you that the number of states of a single string is much, much larger than the number of states of multiple strings. The statistical weight of one string is much larger.
So it's just
So-
the basis of
right.
the
Right. Yes, it's completely based on an entropy argument. And could it be wrong? Of course, it could be wrong, but let me tell you, by now it's been checked in so many cases that by calculating entropy using it, by making the assumption and calculating entropy, so it is a hypothesis. It's certainly not rigorous, and but it's been known for a long time that the dominant configuration of a collection of strings with a given mass is a single string, that it overwhelms everything else. So let's just take that and assume it, and see if we can follow what it says.
Well, that's one of my questions. So this bunch of strings is non-singular.
I don't know.
So let me,
Okay, if you say so.
when you have an equilibrium between the black hole configuration
Yeah.
and the string configuration,
Yeah,
and you do as we said,
yeah.
identify
An equilibrium.
an equilibrium.
A thermal equilibrium? Wait,
Well-
isn't it?
If you say it's G0 is a control parameter.
Yeah.
So I'm going.
So we turn G0 to 0.
Fuzz around.
Right.
At
G,
one point
turn
there-
G0 to 0. There's nothing
There's a
holding.
choice.
Right. There's nothing holding the black hole
There's a
together.
certain critical G0.
Yeah.
Is that when the black hole entropy is equal to the string entropy?
Yeah. But let's right. So what we'd like to do, here's the goal. Let's try to follow this evolution, making it adiabatic. Adiabatic means that entropy doesn't change. And if we can somehow follow it, then we can say but we have to follow the mass. The mass will change. That's the problem. The mass changes. Okay, the
Also,
mass change. That's what we have to
also
make.
the symmetry changes. I mean, you start with the rotationally invariant object. It doesn't bother.
The symmetry changes?
Well, it's like spontaneous symmetry, right? No, that has no rotation.
So it's just an angular momentum zero state of the string. The string is a big ball of wool with lots of fluctuation. Statistically, meaning to say quantum average-wise, look, you could say a spherical atom is really a nucleus with an electron over here. But, you know, spherical atoms are spherical atoms. And, so the quantum mechanics of the string will average it over positions. All right. Okay. All right. Now, the question is, when does the transition happen between string and black hole? given a mass m0, and now starting to vary g, where does the transition happen? So I'll draw you a picture. Again, there is some mathematics behind this. Polchinski and Horowitz have done some real studies of it. But I'll make it short for you. It happens at a very interesting, simple place. Think of the following. Here's a black hole. The first part of this lecture was to argue that strings never really get closer than about one string length from the horizon. That there is a stretched horizon and it's about one string length. So we're going to draw just a child's picture of what the black hole might look like. It's got a bunch of string on the outside. The string loops, each string loop is about one L string in size, and the black hole is enormously big, and it's plastered all over with string. That's a picture. Okay. Now, and that's what one would see from the outside, according to the argument that I gave up there, roughly speaking. Now we start shrinking the black hole. Shrinking the black hole shrinks, incidentally, we're going to see black hole shrinks by making G naught small. In string units. In string units, because of the funny relationship between Planck scale and string scale, you could say it the other way. You could say that in Planck units the string gets big, but you can also say that in string units the black hole starts shrinking, the horizon. Well, it gets smaller and it starts to look like this. In string units, same string units, so the string loops stay about the same size. Eventually, the horizon of the black hole will get no bigger than the string units themselves. Okay? It's pointless to say there's a black hole there at that point. Once the black hole gets to be no bigger than the string scale itself, that's the point at which the transition happens. Now you can check this in a variety of ways. We don't have time to check it. We can check it by calculating the gravitational force on the stretched horizon here, seeing that it's not enough to pull it in anymore. Polchinski and Horowitz did a sort of big study of the dynamics of this, and this is the point at which the transition happens, where it goes from having a black hole character to being a free string. So if we can follow this object to the point where it becomes a free string, then we have a shot of computing the entropy, not by computing the entropy of the black hole, but by computing the corresponding entropy of the string. Okay, that's the goal. Okay, so let's do it.
Can't you done this by varying it G0 and hence big G and hence RF?
G0 is the starting point for some, it's the black hole as we
And then
start.
we change G0 and then we trace the dynamic.
No, we're going to keep G0 fixed, but change G. G0 is just the starting point. Right? You know what I mean? You don't know what I mean.
Not really, no. You have G is equal to G0, G squared.
Okay,
That's when it spins to
let me draw you a picture which I think will make it very clear. I'll show you a graph, and we'll show you what we're doing with what calculation I'm actually doing. All right. Let's draw a graph. M on the vertical axis, G squared on the horizontal axis. Okay? Now what we're going to do, all right, first of all, we're going to pick a black hole. There's a black hole. It has mass m naught, and it happens to be at the point where the coupling constant is g naught. All right? Then we're going to start decreasing g and try to follow it. We're going to try to follow it into this region where the string, where the black hole shrinks to the same size as the string scale. Now, someplace up here, I had the Schwarzschild radius of the black hole, and I've lost it. I had it. It was something or other. Schwarzschild radius equals something or other, something or other, something or other. We could set it equal to 1. That means 1 in string units. And that will give us a curve on here. The curve that it gives us is very simple. The curve that it gives us is just mg squared equals 1. And that curve is the curve which separates black holes out here from strings in here, from free strings, or almost free strings in here. This is the curve along which, for different mass black holes, the more massive the black hole is, the smaller we have to make the coupling constant before it will get to be the size of a string. So for a very massive black hole, we have to make the coupling constant very, very small. For a very small mass black hole, the coupling constant will be pretty big. So that's actually the curve that you get by saying at what point does the black hole become of string scale. Right? That's our transition point. Now, the other thing that we need to know is what the adiabatic curves are. Yeah.
When you say transition point, you don't mean like in the sense of phase transition. This is supposed to be something softer.
Yeah, it's probably this in Bolchinski Horowitz paper. They seem to find in 4 dimensions that it was actually first order with a jump in it. Now that can't really be right. It has to, because it's a finite system. But they did find a jump, but the jump was a very mild jump, and it wasn't enough to change any of the scaling laws. In higher than 4 dimensions, they found it was smooth. Right. So, right. It's not expected that there's a sharp phase transition. Just a crossover from one kind of behavior to another kind of behavior. All right. Okay. Now, the next question is, in this region, what are the adiabatic curves? The adiabatic curves mean the curves along which the entropy is constant. This is an entirely classical question. You're looking for adiabatic invariance. The search for adiabatic invariance is a completely classical question. You simply ask the question, how does a black hole mass change classically as you vary the control parameter g, not g naught, but g? You have a dilaton background, you gradually change the dilaton background and classically calculate how the mass of the black hole changes, and that tells you what the adiabatic curves are. Yeah.
When you go G naught to 0 for a large black hole,
Yeah.
let's say this thing becomes why is this object a black hole?
Say it again.
Why is the object, the string bunch thing, a black hole? What happens to
Whatever. If I take anything and I make gravity strong enough, it'll become a black hole.
Is that a black hole?
No.
It's not.
No.
So a black hole goes into a non-black hole.
Right.
Can you actually show this?
You just take it as an assumption?
Yeah, I think it's a.
No, is this an assumption or something?
Yeah, it's an assumption.
You can demonstrate. You have to take this partial.
It depends on what you mean by demonstrate. If I use all the standard, no. If I use all the standard laws of physics, it follows. Okay? It follows that things have to evolve into other things. If you send a control parameter to 0 and everything else in the system has infinite mass in that limit, the only thing that's left is strings. So yes, I can show it. I can show it, but I am using laws of physics which a lot of black hole physicists don't understand or refuse to understand. Or perhaps they are right and I refuse to understand.
The laws of physics break down to 0.
Maybe, John, given that you only have 7 hours left.
Yeah, we have an hour and a half. Okay. Good. Let's continue. All right, so the next question is, what are the adiabatic curves? And I said, I'm not going to work them out for you. It's not difficult. It's very easy, in fact. In fact, what they are, yeah, they're just the solutions of the classical problem of the mass of the black hole as you vary the control parameter g. And what they look like, I'll write out what their equation is, but what they look like is this. And they cross the transition region. All right, I'll write down that formula for you.
I'm confused because G0 is a string concept and you're working there only with black holes. So
Yeah, but G
there's
squared-
an identification.
G squared is also G.
So it's always with that identification.
Yeah, we're with that identification. That's right. That's right, with that identification. Yeah, exactly. Really, all we're doing is varying G. But the excuse for varying G is that we're doing string theory, so we're allowed to do it.
Yeah,
Right.
not a big deal.
Yeah, so we're really only varying G, absolutely. There's clearly a redundancy of notation. I don't need both of these. Okay, so let me write down what the adiabats are. The adiabats are mg to the 2 over d minus 2 is equal to m naught g naught to the 2 over d minus 2. This is the adiabat which passes through this point. Okay? The adiabat. Everybody know what an adiabat is?
Yeah.
Good, okay. Yeah, I know, you're old enough to know what an adiabat is, but some people learn statistical mechanics before they learn
EV to
thermodynamics.
the campus function.
Yeah. Well, not in this case, but in this case, it's mg to the 2 d minus 2 is constant.
I'm not so sure if you switch to temperature, express the adiabatic,
Yeah.
the adiabat in temperature and make it contact with the black hole temperature, or you might even get something like that.
Well, on this diagram, this is the adiabat. Okay. All right. So this is what you learn from classical black hole physics using the adiabatic theorem and using the idea of adiabats. And you calculate this crossing point here. Once you've calculated the crossing point, now you have, and what about the adiabats for the weakly coupled strings? The adiabats for the weakly coupled strings are just horizontal lines. As long as the coupling constant is very small, the string entropy is simply proportional to its mass. Okay? So once you get over to here, you fairly quickly, and nobody has examined this in any great detail, I think that Joe and Gary studied a little bit, but it just does something like that. They were able to calculate some things in this region here, but basically, we just do that. Once you've done that, you now know the entropy of the thing, because the entropy is proportional to the mass. The mass times the string length scale. You put it all together, the crossing point, and what do you get? You get that the entropy is what it's supposed to be. S is equal to m naught g naught to the d minus 2 over d minus 3 divided by g naught. So up to a constant, up to a numerical constant, the adiabatic following, as you vary the control parameter, gives you the right scaling for the black hole entropy as a function of mass and g.
That's lovely.
Yeah, that, right. Now let me come to the numerical constant. The numerical constant cannot be computed from this kind of argument. Nobody would know how to do it. Not that in principle it couldn't be done. Nobody knows how to follow it in sufficient detail to compute the numerical constant. For example, where this curve is a fuzzy curve. I don't know exactly where the transition takes place. And does it take place when the Schwarzschild radius is a string scale, or does it take place when the Schwarzschild radius is twice the string scale? This will throw numerical ambiguities into the calculation, and so nobody at this point knows how to make the detailed calculation. Instead, I'm going to give you what in some sense is a trivial calculation, but the nice part of it is it gives you some picture of what's going on the horizon. Yeah.
Who can interpret this result like mass of the black hole is related with the mass of state for which you calculate degeneracy by square. So m for the state.
Yeah.
And how could you think about it? It's like
Well,
because
the-
of gravitational. What do you think about it? Because of gravitational energy of the string
Absolutely.
is compensating this bar mass.
Absolutely.
Is just
Absolutely.
correct.
Absolutely. But doing it carefully by following the adiabatic trajectories. Okay. Doing it carefully by following the adiabatic trajectories, along which the entropy should remain constant. Yeah, but no, that's exactly what's going on.
Sorry,
Sure.
what's the question? You can go on.
That by lowering the gravity, it just bigger. Yeah.
All right, good.
No, what Slava said was the relation between the masses of the original black hole and the mass of the string. And what's happening as you turn off the gravity in string units, what was originally an m naught becomes another m, which is basically m naught squared. Yeah. Or in 4 dimensions, right? Right, but it does work in every dimension. You know, one of the reasons for trying to keep the dimensions around is certain odd things do happen in special number of dimensions. I once proved a wonderful theorem about something or other, and I checked it for n equals 1, I checked it for n equals 2, it was right. It only worked when n factorial was n, no. This one works for all d. Okay, so let me give you a totally different outlook on entropy of horizons. This could be the horizon of the black hole, it could be the horizon of ringless space. And the idea is to work in ringless space and to think about what strings are like in ringless space. So let me see, where are we? Yeah. Let's go to the near horizon physics of the black hole, where ringless space is the working tool. There's Rindler Hamiltonian, which I've discussed several times. In Euclidean space, if I think in terms of Euclidean space, then the Rindler Hamiltonian is just the derivative with respect to some angle. That angle is the Euclidean continuation of what I've called omega up till now, which is a hyperbolic angle. I'll think in Euclidean space for the moment. We do thermodynamics by going to Euclidean space, by making time periodic. And so that Rindler Hamiltonian is just conjugate to an angular variable. The angular variable, if the horizon, I don't have enough dimensions to be able to draw, but in Euclidean framework, the horizon is just the point at the polar coordinate singularity. The radial direction is just radial, Euclidean time is angle, and the directions in the horizon, I want you to keep track of the directions in the horizon, they're perpendicular. Unfortunately, I cannot draw 2 of them for you. I can only draw 1 of them. So think about an axis coming out of the blackboard which represents the horizon, and then later I'll draw it for you so that you can see a little better. Okay, let me draw it even another way. Let me draw that other axis in. There's the other axis coming out of the blackboard, and a time slice is a plane like that. As time goes on, as Euclidean time goes on, this time slice goes around like a plane revolving around the horizon. Okay. All right, now I want to do a bit of Rindler thermodynamics. First of all, the temperature is equal to 1 over 2 pi. I'm going to write down some thermodynamic identities. Okay. Next, the free energy is equal to 1 upon beta log of z, where z is the partition function, which I'll just take to mean whatever the partition function for this Rindler system is. This is standard thermodynamics, and the entropy is equal to the derivative of the free energy with respect to temperature. These are standard thermodynamic identities. They're easy to prove, hard to remember. So,
Put a minus sign.
minus sign?
df is equal to minus st dt.
Sorry again?
df is equal to minus
You think there's a minus sign? Well, maybe there's a minus sign here.
You can do a minus sign,
Yeah.
yeah.
Yeah, well, some places a minus sign.
You get a minus sign there, yeah.
Both of them? Well, I'll just change definition.
Okay, so, not used to
Yeah, as I said, they're hard to remember. You're a chemist, that's how you know these things.
Yeah.
I had to learn them the hard way. So if you can calculate, all right, but wait a minute, hold on. In order to calculate the entropy, you've got to differentiate with the temperature. The temperature, of course, is 1 over beta, but beta is 2 pi. How do you vary 2 pi? You don't vary 2 pi. So that means what you have to do in order to calculate the entropy of a horizon is you'll have to put a little conical deficit in here to change the total angle that you go around. Okay. You have to study your system in the presence of a conical deficit. The conical deficit then would be 2 pi, let's see, what do I want to write for the conical deficit? 2 pi minus beta. I want to change beta, which means I want to change the angular distance around here, and to do so, I have to put a conical deficit in at the origin. So studying the thermodynamics of the horizon is equivalent to studying the partition function in the presence of a conical deficit and then differentiating with respect to the conical deficit. At the end, we put the conical deficit to 0, okay? But we need an intermediate step in which we study a conical deficit.
But why you could not? Beta depends on acceleration for inter, right?
What's that?
Beta.
No, beta's 1 over 2 pi.
Yes, it is.
Why did
So
you
you
say
still
equal
can
to
show
1
what
over
it
2
is.
pi?
One at a time.
Uh,
Oh, I know what you're asking. I know what you're asking. Beta is not the proper temperature. Beta is the coordinate temperature.
coordinate.
Right.
So it does depend on acceleration.
That's right. That's right.
Well, that's
Yeah, I was wondering why you don't do the thing with an accelerator that explores the random wave, and they communicate to each other with various accelerations.
Yeah.
So they have different temperatures.
Yeah.
And so you can then get a line on the entropy.
Well,
They're going to see various entropies, and you're going to see how the entropy is a function of temperature.
well, I did that calculation in quantum field theory and found the answer was infinite, and then we had to cut it off.
Not per unit areas.
Yes, per unit area.
Yeah,
There are too many modes near the horizon in quantum field theory.
if you get so close.
Yeah.
So that's difficult.
Right. But we want to do better than that. I want to try to make a more rigorous argument than that. We want to try to actually calculate the missing coefficient here. The assumption being now that the black hole is so big that we can completely approximate everything by Rindler space, and then apply string theory in Rindler space. Now, I want to calculate the partition function. The partition function in this conical geometry with the conical deficit. Let me first imagine all the possible world sheets. The logarithm of the partition function, of course, is the connected diagram. The connected diagram gets exponentiated, so log z just means the sum of connected diagrams. Connected diagram here, the simplest one would be a world sheet with the topology of the sphere. There's a world sheet with a topology of the sphere, and let's think about its contribution to log z. Among other things, there's a conical deficit in here. Let's draw the conical deficit. The conical deficit I'm going to put over here. Missing space over here. Well, that has no effect on this diagram over here, as long as this diagram doesn't overlap with over here. But now, it can have an effect because I have to integrate the center of mass of this diagram around. And the integral of the center of mass around the circle here is going to have a missing piece of angle in here, right? Okay. The implication of that, what is the implication of that? Ah, good. The implication of that is that the contribution of this diagram is proportional to beta. Beta is the total distance around here, right? Beta is the total distance around here, even after the angle has been removed. Since I have to integrate this, the center of mass around the whole cone here, the result is going to be proportional to beta. But a result which is proportional to beta, when divided by beta, is independent of beta, and then when differentiated with respect to beta, gives you 0. So there's no contribution to the entropy from world sheets which, or Feynman diagrams for that matter, same thing would be true for Feynman diagrams, which don't somehow entangle the origin here. It's only the diagrams which are somehow entangled with the origin which will actually feel, whose structure will actually feel a deficit angle. Diagrams like this, or configurations like this, they don't feel a deficit angle. The only way they feel a deficit angle is by the total excursion, the total integral around here, and therefore they will have a contribution which will be proportional to beta. That does not contribute to the free energy. Oh, sorry, that does not contribute to the entropy.
But how does that square with the idea that the accelerator feels the temperature? Wouldn't he say that is an entropy source?
No.
He wouldn't say there's an entropy source.
No. The entropy source is the diagrams which go around the origin.
That's what he would say?
Yeah, that's what it's the ones which go around the origin here. Feynman diagrams.
Oh, I see.
Yeah.
Oh, I see.
Yeah. So, in string theory, it's the world sheets which also somehow are entangled. Let me try to draw one. Let me go back to the picture in which the horizon is a line. It's really two-dimensional. There's this angular space, which is just this plane which turns around. And it's the world sheets which are pierced by the horizon somehow. Now, I'll show you what this means in 2 dimensions in a little while, but for the moment, just think of the horizon as 1 dimension. It's the world sheets which are pierced by the horizon in this way, which contribute to the entropy. Now, how much do they contribute to the entropy? Okay, the argument is indirect. Although I did do a numerical computation with a computer, putting a bunch of points on here and integrating and so forth, and got the right answer, very close to the right answer. But there's an indirect argument. And the indirect argument, let's just take world sheets, begin with world sheets which just have the topology of a sphere. Okay? What I'm interested in, and what do they give? These things are the things which give the effective action in string theory. The sum over world sheets like this give the effective action in string theory. The effective action is the Einstein action, or at least the Einstein action on large scales. On large scales, and we are on large scales because the black hole is supposed to be very big, on large scales, this will give us the Einstein action plus corrections and so forth. That's what this gives. But what is the Einstein action for this geometry? The Einstein action is, of course, just integral r. There's also some surface terms which are not important. The integral of r, the curvature. There's a curvature singularity along this line. The curvature singularity along this line is because we have set beta equal to something not quite equal to 2 pi. Okay. So there is a curvature singularity which is proportional to the conical deficit along here. If we integrate this up, there's all the usual stuff, 1 over 8 pi, I forget what's there. And we integrate the Riemann curvature here, or the Ricci curvature, the thing that goes in the Einstein action, we integrate it over this region. The only place we pick up a contribution is from the conical deficit on the horizon here. What is it equal to? Well, it's clearly proportional to the area of the horizon, okay? But it's also proportional to the conical deficit, 2 pi minus beta. It's got a 1 over 8 pi in it. It's got a 1 over g. In the Einstein action, there's a g downstairs. There's a 1 over 8 pi g. What else? And this is just straightforward general relativity calculating the effect of a curvature along that line. Looking for the answer. Oh, yeah, that's it. That's log z. That's what you get for log z. What you get for log z divided by beta is this. And that's it. 2 pi over beta minus 1 divided by 8 pi g. Okay. Well, now we can calculate the entropy. 1 over beta is temperature. We can differentiate with this with respect to temperature. 2 pi divided by 8 pi is 1 over 4, and the answer is 1 over 4g. Okay? This is not a surprise. This is not a surprise at all. There's nothing surprising about this. But what it does tell you, so let me tell you what I think it tells you. It gives you some picture of what the degrees of freedom near the horizon are, which are accounting for the entropy. So if the entropy is all being accounted for by world sheets which pierce the horizon like this, then let's look at the system at an instant of time. An instant of time, an instant of ringlet time, now means take a surface like that, slice it, and see what you see at a surface of time. What you see at a surface of time is a string. You see a string, an open string, with 2 ends attached to a membrane. The membrane, in this case, just being a line. That's what the configurations at an instant of time are that have to be evolved to give you the full partition function. Strings connected to the horizon as if the horizon were a membrane, as if the horizon was some sort of brain. If the horizon is 2-dimensional instead of 1-dimensional, then the configurations which contribute are, again, strings just attached to the horizon like that. That's why I like this calculation, because it gives you some kind of picture of what's accounting for the entropy in string theory. This argument about open strings predated all of the D-brane calculations and so forth. But again, in D-brane physics, again, it's open strings which account for the entropy. So if you believe all of the steps, then the calculation of Schwarzschild entropy is really, in many senses, much simpler than any other example. You don't have to know a lot about conformal field theory and so forth if you believe all the steps. And I, frankly, find the steps at least as believable as the ones that go into the extremal black holes. But the extremal black holes, the point is the extremal black hole calculations are so hard and so difficult and so full of subtlety that when you get the right answer at the end, you say, aha, it must be right. It's interesting. Paradigms change often when somebody does a calculation that nobody can understand but gets the right answer.
So,
When you can understand when there's no mystery.
but then I do not understand why people get so excited about the field of hope if there is this nice picture for any hope.
And is this number?
I'm telling you what. It's because hard calculations can go wrong in many places, And when they don't go wrong in many places and wind up giving you the right answer, you have a right to boast and say something non-trivial
I
happened.
understand, but
But that's-
hard calculation is not the most.
Look, all of the methods rely on the same trick. They all rely on this trick.
Yeah.
Nobody ever calculates directly a black hole. What they do is they take the black hole and adiabatically vary until they're talking about some free field theory or something, till they get to some place where they can calculate, and then do the calculation.
But what actually hard extreme of the hole has to do with these calculations? That's the problem, because in extreme of the hole you are getting extra L factor because of central charge, which counts you actually
Yeah.
right of different configuration.
Well, I think for extreme black holes, you simply have to start over. The structure of the horizon is not Rindberg, as you well know.
Yeah.
And I think you simply have to start over. I'll tell you what the nice thing about, what's different about extreme. These strings here are at high temperature. The fluctuations in them do not decouple. There is no reason to think that this is string theory at very, very low energy. It's string theory at the highest possible temperature. So the fluctuations of these strings don't decouple. If they did decouple, I would be able to do a different kind of calculation and do a direct Hamiltonian calculation. So the strings that we're talking about here are highly excited in general. What happens near the horizon of an extreme black hole is the temperature goes to 0. All right? So that means that the strings that account for the entropy are basically unexcited strings, and you do the calculation by field theory. That's the thing about extreme black holes, that the temperature is 0 near the horizon, and the quantum mechanics of the strings are simple. They're just elementary quanta.
You also need exact vicinity.
Yeah.
It only occurs at 10%.
Yeah, absolutely. Well, I don't know. There are people who say they know how to calculate some extreme black holes when they're not completely supersymmetric, but I haven't followed that, so I don't know.
How about Bekenstein Hawking? You were advertising.
Well, what we're saying here, what all of this did, was the Bekenstein-Hawking entropy is by definition the area divided by 4G. Okay? Now, there's a good reason to think that's really entropy, of course. Right? But what one wants to do is see that it's connected with state counting, with real state counting. And so the first example that I did, which is the real state counting calculation, was to count states of the adiabatic evolution of the system into a collection of free strings. Right.
What I'm confused about, here there's a tendency to attribute the energy to the entropy to the space. However, when you study the accelerated observer, you can do the detailed balancing, as you know, the accelerated observer can emit a photon,
Right.
because it is accelerated.
Sure.
And then you're looking at something that you would attribute to the energy due to the vacuum fluctuations,
Yeah.
which he is experiencing without reference to the space, but with reference to how he experiences.
Okay, but in the Euclidean picture, yeah.
Contact.
In the Euclidean picture, what we're talking about is also vacuum fluctuations, but it's the vacuum fluctuations which are sort of half on one side of the horizon, half on the other side of the horizon.
And what's going around there?
It could be anything. It could be. Let's say a quantum field.
Okay.
All right. A quantum field will give you an infinite answer, but let's just ignore that. Okay. A quantum field will give you an infinite answer that the string won't. But
Unless you cut it off.
unless you cut it off. But let's just think. It's the objects which are accounting for the correlation between the two halves of the space.
Yeah.
Right. And so it's got to be things which somehow circumnavigate the. Right. Yeah.
But you see, if you look at an independent event, then you use detailed balancing.
Yeah.
And then you compare the entropy of the source of the heat before and after the event.
Yeah.
You know what I mean? The
Yeah.
ratio of absorption,
Mhm. Yeah. Okay.
the Einstein coefficients, and then you have the change in S. So you find that it dt, that P df is equal to
Yeah.
dn.
Right.
So there you're really looking at the vacuum fluctuations itself, and here you're more focusing on the geometry of the space and
Well, I'm saying that the vacuum fluctuations are what lead to the effective action.
Mathematically, that's how you do it.
Yeah.
And that's how you get the spontaneous emission of a ground state.
Mhm.
Right? I mean, a ground state spontaneously emits
Mhm.
of an accelerated observer.
Mhm. Yeah.
And you do make this
Yeah.
contour.
Right. But another way of saying the reason that you've got to the reason that we know you have to circumnavigate this, and if this doesn't contribute to the entropy, is because if it did, there would be a lot of entropy far away from the horizon. And we know there's no entropy far away from the horizon. So it's the entanglement of the diagram with the horizon, which is the source of the
That's
entropy.
absolutely essential.
Right, absolutely essential. It took me a while to realize that. I kept getting wrong answers. But. Okay. Thank you.